I don't want to, have this talk be really boring. And it's pretty straightforward and a simple talk, just like the blog post that I've written. It's straightforward. And I don't want to bore you guys with a lot of slides, hence it's minimal. It just, consists of 18 slides. And I structured this in such a way where I could probably, go over what tokenization is, the different type of tokenization. And once that is done, I'll probably go over my implementation and talk about the design choices, about how I implemented the code, and finally end it with a piece of advice regarding low-level implementations, considering I do have a bit of experience in implementing all that. So yeah, so I guess it'll be interesting, and hope you take something from this talk as well. And before going over the talk, let me introduce myself. I'm Ashvanth. I'm currently a final year undergrad at Ashvanth University, Chennai. I am currently doing my internship at a startup named Pibit and also a research intern at IIT Indore. So yeah, that's from my side. And guess I will go over my talk. Do you guys want me to present it like this or present it from that aspect? When? How do I go
Whatever
about
works
this?
the best for you.
Well, chalo then.
You can try
Let me.
presenting it that way. You can see.
Yeah. Obviously, I can.
And if you don't feel it's that smooth, you can just go back to this.
Well, let's see. If it's not, let me go back and yeah, let's go to the content. So, okay. The first one, the topic is about tokenization. Since we are talking about byte pair encoding, I felt it's important that we have an review about what tokenization is and what are the different type of tokenization methods out there. So starting off with what is tokenization? Simply put, let's say you have sequences of text and you want to feed your model. And models aren't humans generally. They do not understand text like we do. They do not connect the sounds and then they don't get to learn. They deal with zeros and ones. That's how computers are made. And that's the language that they understand. So you have to convert the sequences of text to numbers. And that is the entire process of tokenization, where the first step and the last step of the text processing and the modeling in NLP. So why is it needed, you might ask? And simply put, as the question already answers it, the major goal is to make sure that the model is able to understand the text. Hence, you basically split the input text into a sequence of tokens. And what are tokens? They are basically an atomic piece of text. And hence, the start of tokenization dates long back. They were really simple, straightforward approaches. In fact, the chalk should have been kept as a modern and an elegant version of tokenization, because that's what BPE is, byte pair encoding is. And the first tokenization method that we'll take a look at will be word-based tokenization. And word-based tokenization is quite straightforward. It is direct, where generally given a sequences of text, you get to split the sequences based on the words or the white spaces. And you get to split it based on words with the presence of the white space between the words in them. And however, there are certain where, let's say you go take a look at the Spacey library, which is widely used, something that I get to work very often with. They have certain rules in implementing the tokenizer. Guess you have the access to the slides, you can probably take a look at the documentation as well. It has a really good explanation regarding the rules which they have implemented it. However, with the word-based tokenization, there are limitations. And what are these limitations? Limitations is the fact that you cannot have a larger vocabulary size. You cannot assign an index to an individual words or to unknown words as well. And then processing unknown words is a major problem. Since there's a shorter vocabulary size, how would your model eventually deal with new words that might be added? And hence, there's an approach to solve this problem. And this was via the use of an unknown token in the vocabulary. But again, think about it. Using unknown tokens for a lot of words which aren't present to the tokenizer initially makes it really difficult because you lose a lot of information that way. Also, it trains as different words, different unknown words, same. And it leads to increased memory usage and also leads to a lot of training time. which is seriously a problem, and it also does not lead to good results. And this is when they had the next approach coming in, which is the character level tokenization, where earlier in word-based tokenization, you get to split the sequences based on words. And here in character level tokenization, you get to split the sequences based on individual tokens and individual characters. Sorry. And there'll be no or very few unknown words present in character level tokenization. Also, fewer number of tokens will be used, considering the fact that you are operating on single characters. And it's quite straightforward again. However, same thing, there are limitations in this approach as well, where the major limitation is the fact that there is no understanding of a semantic context. There are like various words, but then since you're processing each and every word present in the sequence via a single character, you wouldn't be able to understand the meaning of a particular word and the semantic no surrounding regarding the word. And also the fact that let's say you have an input sequence consisting of 10 words. This is fairly simple, and each word, let's say an average of 3 to 4 words, you have a smaller vocabulary size. But then generally with large language models, that is not a goal. You're going to feed it with a lot of data, and with a lot of data comes in long sequences. You can't be using a character level tokenization where you process each and every token. And this is when there's this improved and probably a better approach that came in called subword tokenization. And before that, let me if any of you guys could guess this. It's also written in my blog post if you do remember and had read it. This is a game of Tetris, and this might be an analogy for you to understand how subword tokenization works. Guess you guys would have played Tetris during your childhood. I'm not too old, not too that young as well, but yet. Tetris is a game where you see blocks literally falling down from the sky, and then you see various blocks of various sizes coming down and then merging together, and then eventually they get to vanish. That's how Tetris works. And the same way, subword tokenization as well works similar to Tetris, where frequently used words would be split into subwords, and we take the most commonly occurring words, take them, replace them with another alternative character. Then the next group of characters will be concatenated together, and you repeat the same process. You see, let's say you have a different an input sequence of varying length. You find the common characters which are present, and then you take another alternative character in order to represent these common pairs of characters, and then modify them. And yeah, is there any doubt as of now? When can I proceed?
Oh, yes, please go ahead.
Yeah, sure, thanks. So, that's how it works. You take, again, you find the pairs of common occurrences of these tokens, you replace them with an alternative token, and then this process continues until you can call it a hyperparameter, where you can define how long should it continue, or let's say you have literally exhausted all the merges that can eventually take place in the subword tokenization process. It was first introduced in this 2016 paper called Neural Machine Translation of Rare Words with Subword Units. You can probably read the paper sometime later. And it's pretty much the common approach currently used in all the model language models that are currently present, right from GPT, T5, Roberta, Llamas, Mistrals, you name it. But again, there is a variation of the subword tokenization algorithms used by these organizations and in their models currently. And let us probably take a look at them as well down the line. I'll probably give an introduction to it. Feel free to read in your free time. So first, let me explain you with a piece of example so that it'll be easier for you to understand how the byte pair encoding works. Let's say and again, this example is a really dumbed down, really straightforward example where we are doing a character level byte pair encoding approach over here. And take an example where this is your entire training corpus. You have few words where there are, let's say there's this word called low, there is something called wider, and there's a word called new. And let's say how many, the total number of words is 5, no, 6, there's 2 over here, and there's 3 over here. And understandably, we want to have a subword tokenization algorithms generally have a starting and an ending character delimiter so that they would be able to distinguish the sequences they get to deal with when they start and when they end. And in an example as well, we'll use this backslash e as our delimiter. So here we take an account. We have low to be of 5 times, lowest 1. And there's a count of 2 of wider, 3 of wider, and then 2 words representing new. And your vocabulary would be the, as explained before, we are dealing with character level subword tokenization. Hence, we'll be dealing with individual characters like /e, l, o, w, and the rest of the characters out here. And next, the process would be to identify the common occurrences of the pairs of tokens. If you probably take a look at them, you would see how there is W and E, the ending delimiter, occurring commonly. You can see them occurring 5 times and 2, which totals to 7. And hence, you'd be merging them and adding them to your vocabulary. Once that is added to your vocabulary, you would then replace them in your corpus. So now that you have replaced them in your corpus with W and /E together, you replace at both the places where they occur. You next take a count again at your corpus, where you could see that L and O gets to appear here for 6 times respectively, compared to the rest of the tokens which are present here. And now the process repeats again. You get to add them to the vocabulary, and once they're added to the vocabulary, you go merge them and replace them with an alternative character. And this is how it is. And this is how byte pair encoding works. This is a fairly simple and a straightforward example for you to understand. You can try it with your own training corpus, use a pen and a paper, use a few words, see the occurrences of the common characters, merge them, add them to the vocabulary, replace them in your corpus, and then continue the process again. So let's say a new word called lower is present in front of a model. So once a word like lower appears, your goal is to now split them into respective tokens. That's what the tokenizer does right now. After having learned from the corpus, it gets to split it based on our vocabulary, because we have LO being merged from due to the presence of all these words in the training corpus. It was able to learn, and then it's been added to the vocabulary, and now we get to add them, and helps in splitting the word lower into LO, which is then merged into a single token, and you have W, E, and R as a separate token. This is the only merge out here. And there are other subword tokens. This is a fairly straightforward. The previous slide was a straightforward example of byte pair encoding. There are other subword tokenization algorithms like word piece, and it was introduced in this conference called ICASSP in 2012, where the merges were again same place, same way like in BPE, which the example which we saw. But again, there's a minor variation, just the fact that previously we used counts of the words or the characters over here, but here we get to deal with the probability of the occurrences of tokens. That's how word piece works. And then sentence piece is completely different. They perform tokenization without pre-tokenization. They are beneficial for languages without no word boundaries. And you can also take a look at the paper. It's linked over here. It's a really great paper. It's also used by Llama 2, I think. I haven't read the Llama 3 report as of yet completely, hence I wouldn't be able to comment on that. But I remember sentence piece algorithm being used for languages where you wouldn't be able to split words based on their sentences, on the white spaces. And it also helps in performance in those languages. But again, are there any limitations with regards? Just like any algorithm which is developed, as much as the advantages that it gives, there are a few disadvantages as well, which is it doesn't work for languages like Finnish or Turkish. And why it doesn't work? Because it consists of words where a single morpheme has a morpheme meaning a single token which has a semantic meaning towards. And these are languages where there are individual words without spaces, and it'll be difficult for the tokenizer to understand how it works. And also other pre-tokenization rules doesn't apply to these languages. With that being said, let us now proceed to implementing byte pair encoding in C. I will also link my blog post. If you guys haven't read the blog post, do read it in your free time, not now, because I'll be explaining over it. Yes, I think once I complete my explanation, you'd also have a really good idea regarding the design choices in it. So with regards to byte pair encoding, as I said before, you have three major processes. One is you get to train, and the training involves encoding and the decoding. The decoding comes at the latter part of the process. First, you get to train your tokenizer on a set of corpus. You get to encode the text, and later you get to decode it. So first, with regards to the implementation, you have few necessary header libraries which needs to be present. And let me probably come out and share the code. I think that would be easy for you guys. Yes. Yes, the screen is visible. Yep.
You may want to increase the maybe the font a little bit.
Size.
Yeah, just do Control plus. See if that works.
Oh.
You're using VS Code, right?
Yeah. Is it visible right now?
Yes, it's much better.
Or do you want me to increase a tad bit? Right?
Oh no, this is perfect. Actually, at least I'm able to see it. If everybody else is, I think.
Probably you can type it out in the chat over there. If you guys aren't able to see, let me know how
Actually,
the
there are some
responses were.
questions in the chat too.
Oh, there are questions in the chat?
Yes.
Oh, yeah, go ahead. Let me probably clear those questions and then we'll proceed to explain this. You can probably read the questions.
Are you able to see the questions?
Oh, wait. Just a minute. Let me probably take a look at the questions.
The first question is, the original characters are still left in the vocab along with merged characters.
Okay, wait. Again, see, my example is really limited and straightforward. Eventually, when you have a larger corpus, you would have merges taking place, lots of merges taking place. Again, as I mentioned, it is a hyperparameter. It is up to you to decide if you want to end your merges depending upon the total number of merges, not exhausted, or rather implement it for a few box as such and then stop it out there. In our example, you could see I only have a few words, and hence there are a lot of unmerged characters which would obviously be present. So yeah, hope that answers your question. And the next one would be, in this example, low occurs 6 times as well. Is that also merged and considered in the vocabulary? Let me probably take a look. 4, 5. Low occurs for 5 times. And guess again, see, as per your doubt, it goes back to your previous answer. It occurs for 5 times over here, and you have to consider pairs of tokens. And I just exhausted so that I do not add extra slides explaining the same process where you get to identify the pairs of tokens which are occurring commonly and then merging them again and then adding that to the vocabulary. Hence, it was present like that. So hope we are good to go. Yep. And are there any more questions? Yes. Guess not. Well, let me then move over to the explanation of the code. So first, we'll have a few basic assumptions, which is assumptions in sense with regards to vocabulary size and the maximum text size, which are getting to deal with in this implementation. So the first point would be these are the major imported libraries. These are standard libraries present in C, which is dealing with the input and output, for taking an input and also returning an output. And this is for making sure that you get to deal with strings. And this is for making sure you get to specify the length of the sizes of the vocabulary down the line. And that is done, and we'll proceed to probably the assumptions. The vocabulary size here, since as I mentioned earlier, it's a fairly simple and a straightforward implementation of it in C. Hence, I limited the vocabulary size to assume only 256. Generally, all the tokenizers implemented by, let's say, Llama, Mistral, have a vocabulary size which is really, really huge. GPT-4, I hope I'm not wrong. GPT 3.5 was 50,257, and GPT-4 obviously crosses that. I heard Llama 3 or Llama 3, yeah. Llama 3 was around 32K, the 70B version, and after that it had been increased to 128 or more than 28K as such, in case I'm not wrong. But yeah, generally the vocab size for all these large language models are really huge. They take in lots of sets, right from code to code consisting of no HTML tags. There are a few interesting papers out there as well, which says training on all these code helps in merging way better, and that is an interesting aspect to think about. And so yeah, once that is done, there are a few more important structures that we have to define before we proceed to the major part or the chunk of the code, which is we get to define the structures of which might be used down the line in the code. First is this called int pair. This is basically present for representing a pair of integers. In with regards to the context of byte pair encoding, since you're taking in pairs of tokens, you're going to assume the first character and the second character. Hence, this was present. Next is the merge, and this is extends this structure extends the int pair structure, and then also adds in an index as well. As we merge pairs of tokens, we create new tokens that are added to the vocabulary. Hence, you need this structure as well. And once that is done, this is here, and this plays a major role. This is what the code is composed of. This structure is called basic tokenizer. That's how I defined it, and it takes in or it extends the merge operation, gives a pointer to merges, and then you have other parameters like the number of merges, and it also consists of the vocab which you would get to implement, which you get to have down the line, and also the vocabulary size. So yeah, and once that is present, we would first initially we'll get to first implement a tokenizer. We'll create it, and then we'll see how to go about training in the training process where we'll encode and then decode it. First, we'll create the tokenizer, and in this tokenizer function, you get to first define the tokenizer. You have a pointer defined to a tokenizer where you allocate a memory to it. For all those people out there who are probably, since personally I have been coding way too long right now, but still coding in C. I probably coded in C back when I was in my first or second year, and after that I didn't. It was quite a long time since I went back to code in C, and there's often this confusion with regards to pointers. So a small refresher regarding pointers. If you guys have a doubt, there are way too many good resources out there available online for you to understand. But yet, let's say assuming you have a system and any system has a memory, and with regards to a memory, you have an address and a value. An address represents a location, and the value out here is the data stored in the location. So pointer, simply put, is just a value that happens to be an address. You have an address, you have a value that points to another address. That is a pointer out here, as simply explained as that can. And hence here, you are creating a pointer to a basic tokenizer where you allocate a memory to it. And then you initialize the merges with null. And then the total number of merges as of now, as you're creating, is 0. And then you also allocate memory to the initial vocabulary size. And then you loop over, and each element of the array will point to single character string. And once that is done, vocabulary size is initialized, and then you return the tokenizer. That is it. It is just a simple tokenizer, a function where you create it, allocate memory to it, allocate memory to the individual tokens which you might create on the line. And since we are writing the code in C, it is a really good practice that once you allocate memory to it, by the end of the function, or once the function is used, you get to free the memory. Down the line, hopefully it doesn't cause any segmentation fault, or it doesn't stop your program because the memory is already allocated, and no, it doesn't cause any issues with regards to that kind. Hence, it's good that you implement a function to clean the memory, and hence this free function is used. Hence, it cleans or it frees down a block allocated by the malloc, as is explained here. With that being done, we get to create a basic tokenizer, we get to use a function. And let me probably run and show this to you. We compile it, and once that is compiled, let run. Yes, we have successfully done it. You have created a tokenizer, and then you have initialized a size to it, which is 256 as explained earlier. And then once which is done, you have also cleaned or freed up all the memory. So now that the training process is over, we'll move into the byte pair encoding major chunk of the code. So yes, now that is done, we have to go over to the training part. We need a few helper functions with regards to the training function which we'll implement. One is that we'll be needing token counts. That's a function out here, which is used to count the number of tokens, simply put, in a single line. And then next, you need a function called merge. It merges the tokens and updates the array with new tokens. And after that, in the merge operation, you would also need to find the pair of tokens which are present together. Hence, you also have a function implemented for that. So first, let me go over to the token counts function. You have a few parameters like a token array of token IDs and a number of token IDs in the array, and also an array to store the pair counts. That is basically the first token and the second token which occur together, and also a pointer to store the number of unique pair forms. Okay, so with that being done, let me go through the main chunk of the code. Now you have a pointer which is being initialized first for the pointer to store number of unique pairs, and then you loop over the character IDs in the ID arrays, stopping at the second last character to see if there's any outer bound access there. And then you find the pair of tokens which are commonly present together. And then once you find pairs of tokens which are present commonly together, if the pair is new, you add it to the pair counts array. If it's not new, you just increment the count of it. If it already exists, you increment the count of it. Note you'll have a better view of the train function once I proceed to the other helper functions out there. So once the token count function is over, let us take a look at the merge operation. Before the merge operation, yes, the find pair index is used in the merge pair. If you take a look, wait. Okay, let's just go to the merge function right now. Merge function has a few parameters, which is basically an array of token IDs that has to be merged, and then a pointer to the size of the IDs in the array, and a pair of tokens, which we are extending the structure present here, and then also an index array to replace a merged pair. First, you initialize new IDs with a maximum text size that you are initializing it over here, and then you loop over it. You find the pair of tokens which are commonly occurring. You see the first pair. Once that is found out, and then you find the second pair of token. Once it is found out, you get to append it to the token size. Else, you just increment it. And once that is done, you copy it, and then you allocate the size to it. That's it. The merge operation is quite simple. You find a pair of tokens which are occurring together, and then you just add them to the array. And the find pair index, simply put, it decodes a list of token IDs back into text. Same, you get to find this is used to find the pair of tokens, and the merge function uses this one in order to merge all the tokens which are found together. So since the helper functions are explained and it's quite simple to understand, we now proceed to the train function. Train function probably takes in the major chunk of the code. It consists of, it extends the tokenizer structure, and then the text which is being taken as the input, the vocabulary size, and this is a parameter which can be implemented or cannot, depends on you personally. I just wanted this because I felt it's again a design choice. I wanted to have this a PyTorch or a PyTorch in deep learning. When you generally train anything, if you want to see the output being exist, you would add a parameter. No, I wanted to implement that sort of approach in the implementation as well. Hence, I added this parameter. If you give 0, you wouldn't have any printing of the merges which are taking place down the line when you run the code. Or if you give 1 to this, major goal is that it will print the merges which are taking place. So same way, you initialize a number of merges. Basically, there's a vocabulary size that you have initialized. Generally, this is 256. That is the initial vocabulary size. And this vocabulary size is something that you get to give out there. And then you find the text size, the size of the text which is present as the input. And again, since it's a really minimal and a small implementation, the size of the text is also really small. And once that is done, you go over, you allocate memory to the merges operation, and you calculate the number of the merges. You uh, loop over each merge, and then you count the number of tokens present in them. And once the tokens are counted, you see the pairs of tokens which are commonly occurring, and then you see if the count is greater than the maximum count. If it's greater, then you assign it to them, and then that's over. You add them into the vocabulary, and else there are and finally, let's say this is an exhaustive list, and this 3 represents generally is a design choice. Again, I felt I could have implemented this better, but at this point I just left it because it's pretty much done and just works for this minimal implementation. Probably if any of you guys are really interested, you can go ahead and modify the implementation, make it look way better and also work, can optimize the code as well. Go ahead. So the 3 represents basically, I made sure this array takes in, it's a flattened 3D array where the first represents a count of the presence of the first token. The second index represents the presence of the second token. And the last one, third, represents the count or the occurrences of these 2 tokens together. So hence it is given as 3. And also this loop, it ends once there are no more merges to take place. And once that is done, you get to allocate the memory over here for the tokenizer. You get to perform the merge operation for all the tokens which are present, and then you get to perform or allocate the memory to it, and you get to print it. And as usual, as I said, you just get to free the allocated memory once you have done your operation out here. Once that is done, let's go over right now and look at the encode and the decode operations as well. The encode operation is basically, as said, you have sequences of text and a machine is not able to understand strings which are present there. Hence, you try to convert them into numbers, and that is what the encode function is used over here. You get to count the number of occurrences of each tokens, which are occurrences of the characters present in the input sequence, and then find the index of all these characters, and then get to merge them. And that's what the encode function is used to do. Take a sequence of text, convert them into numbers. And once the encode function is done, we move over. And this is the final function where there's this process called decoding. Basically, the reverse of the encoding process, where you take a sequence of text and then convert it back. Take a sequence of numbers and convert it back to text. You take from the vocabulary, you get to convert it back into text, and then you just add the final delimiter operation over here. You just add the character. That is done. So pretty much the entire code is extends about 300 lines, within 300 lines, and this is the final piece of it. You get to initialize the tokenizer, and then you get to have an input text out here. You define the vocabulary size, and you train it. Find the common words which you already have a corpus. Imagine 256 ASCII characters, and then you go over these characters, find the common ones, append them, and it ends. It's exhaustive. You encode it, and then you decode the IDs finally, and that's what you need. So to give a final mutation, compile it. Smash. Yeah, that's it. So fairly a simple and a straightforward implementation. You have a piece of input text. There are few merge operations which are taking place where you take a look at the text, you find the common words which are present. These are merged, and these are the encoded IDs for each text. Let's say, assuming we'll do it for a simple letter 2-word. You compile it again, and then you run it. You see, this is how it works. You find again the common piece of characters which are occurring together. These are the encoded IDs, And then finally, you get to decode it using the decode operation out here. And as usual, this clean tokenizer can be removed, and still I feel it wouldn't cause any issue, hopefully. And yes, it doesn't. But yeah, it's a good practice that you generally have get to clean the memory after the function ends while implementing in a low level language like C, where it doesn't deal with no the memory really good like Python does. And yeah, we have come to the end of the talk as of now. And a final piece of advice which I would love to give is that for all those folks trying to implement low level implementations of any function, or let's say there's this code like let's say a model like transformers, vision transformer, anything of that sort. First things first, understand or have a strong why as to why to implement, a reason to implement it. Because often in Twitter, I see people out there not having a concrete goal. It's also a generic piece of advice. Because when you have a strong why in your approach, you would get to accomplish what you set out to. And hence, initially, for implementing this, my major goal was because I wanted to understand how to build a large language model for my mother tongue, Tamil. And generally, all these language models currently do not work with other low resource languages. And Tamil, as such, even being the oldest language, it does not have a really good data out there, and hence it is not properly or adequately represented in all these models. Hence, I wanted to understand that process, and eventually ended up learning how transformer works from scratch. And in that, I was not able to understand byte pair encoding in detail, and that's why I implemented this from scratch to see if I was able to understand. Now I feel that I do have a fairly good understanding of how it works. So hence, I would ask you guys to have a really strong why as to implement it, and also try blogging about it, like what I did. You may never know, because I got this approach because Finn read the blog and then contacted me. So also writing makes you think clearer. It also refines your thought. It will explain things really well. Hence, write about the things that you get to implement or read about. Think as a sort of creator that would make things easier for you in defining your approach as well. So yeah, thanks for the opportunity, Vin. And if you guys have any doubt, you can ask me right now. Yes, you would not have any doubts, considering the fact this is really straightforward. I also explain the design choices. But yeah, any doubts? Or we can end the talk as well.
Um, I think one question to ask is I know you were going
Yeah.
for efficiency. You coded in C for that reason,
Yes.
implementing.
Yes.
Um, have you tried any other languages at all?
Okay. I wanted to try it out in Rust. But then once I implemented my blog, no, once I published the blog, I had a few people contacting me and telling how did you do it? What was your no? Why did you do it of this sorts? And they did DM me quite a few times, and I explained it to them. And within a few days, like 2 to 3 days, I had them replying back saying, "I implemented this in Rust. I implemented this in Zig, and I have no clue about how Zig works or how the syntax of Zig." But again, I have these people telling that they implemented it in Rust and Zig. I thought, well, that's good. Probably I inspired a few people out there, even if it's a simple and a minimal implementation. I inspired them, and those guys get to implement it in a language of that. And hence, I felt that it's fine. Probably down the line, if I get to implement something different, I would probably implement in Rust or so. Yeah.
Oh, that's cool. What about maybe like Mojo or Julia?
Oh, yeah. I do not have any experience with Julia. I wanted to implement in Mojo because I remember when the first time Mojo came out, no, there was a lot of buzz around it. I remember Jeremy Howard tweeting about Mojo and no, no, looking forward to that as well. But again, C was probably the most intuitive thought for me because I had a really good exposure to C and how I can code in C as well, much better compared to Mojo. Hence, I felt I would just go ahead implement it in C. And again, there was few issues of memory allocation which I constantly got to deal with. And since I was rusty as well, Claude really helped me out there. Without Claude, I would have struggled with dealing with the memory issues a few times.
Oh, that's awesome. Thank
Yeah.
you so much for presenting.
Yeah,
Does
yeah,
anybody
thanks.
have any specific questions? If you can just keep on presenting, if that's okay. Just the
Oh, yeah.
presentation, not the.
Yes, just a minute.
Folks, if no one has any questions, I guess 2 quick announcements. I think everybody knows we're looking for more NLP leads if you're interested.
Yes, did
And
sign up for that.
okay, cool. And second, I believe if you have any feedback or you would like to see more
Yeah,
in our reading groups, I would love to hear it. Give me a second. Let me actually switch off the recording so everybody feels comfortable
yeah,
chatting.
sure, sure.
Uh,